Now.
Now.
Hello?
Hello, everybody.
Can you hear us?
Hello,
good
yes.
morning.
Okay, good
Hello?
morning.
Perfect.
Perfect.
Okay, great.
Good morning. Thank you.
Well, so
Okay.
you are going to share here your presentation?
With this okay. System.
This.
Eufemia.
No, to reopen
Eufemia.
this. Okay. You have this presentation in the
Yeah,
desktop?
for me, yes.
The desktop? Okay. Let me just start again. This one. No?
Yeah. Okay.
Okay.
Can you see the presentation?
Yes.
Okay.
Okay, thank you.
Maybe we don't have them very well because some of them have percent in virtual. So, but it's too low.
Yeah, we can try these speakers and this one and choose between them because the sound is not very high. So when it's their turn, we can check
Okay.
as appropriate. Okay.
Okay. After my presentation,
yes.
there will be the virtual presentation.
Okay,
so,
no problem. Now I think they are going to hear
Okay.
us correctly, but then we are going to.
Okay.
Okay.
Ok. Sì. Probably no, ma sta lui qui con noi. Okay. Welcome everybody to ICCSA conference. We are starting our session in our workshop named Geomatics for Resource Monitoring and Management. My name is Eufemia Tarantino, and I'm the author of the first presentation with Mirko Saponaro. I come from Polytechnic University of Bari, and for me it's a great pleasure to be here to present our work. Our work, the name is Land Use, Land Cover Classification Performance of Supervised and Unsupervised Algorithms on UAV ortho mosaic. Okay, we can start. When the geomatic researchers use UAV data for the territorial monitoring, in absence of remote sensor data at a specific acquisition time or period, for example, or in case of making further insights on a specific studied area. And despite the advantages of using UAV and low-cost sensors, it is necessary to address the limitation and to analyze the impact in the data post-processing stage. And there are the needs of a robust analysis of the LC classification based on visible bands, and this is not widely addressed by the scientific community. We are used to process multispectral data and usually no, è italiano.
Allora io ero libera, quindi se ti serve una mano
sì.
sono qua.
Ok.
Okay. Ma non ha sedia?
Sì, solo la prima la prima slide.
Solo la prima slide.
È possibile. Non lo so, non è colpa mia. Dai. Ok? Dai, mettiti tu qua.
No, stai. Ma hanno cominciato?
Sì, abbiamo cominciato e si vedono solo quello.
Ora vedo. Questo è un problema del loro computer, non di questo. No, dice che vedono solo la prima slide, non va avanti la presentazione. Ok, proviamo a interrompere la condivisione. Ok, allora devo fare così, layout, cliccare qui Ok, riproviamo. Clicca
Sì.
un'altra volta qua. No, prova a fare questo, soltanto questo qui, compatire. Apri PowerPoint, mi permetto di darti del tu.
Certo.
Prova a cliccare qua. Vedete se lo vedono adesso?
No. Non
It's okay.
ancora.
Are you seeing the
Not yet.
slides? All the slides now?
Not yet.
Not yet. It's a problem. In this room, it's a problem.
Ma è strano.
No, ma non c'entra. Non è possibile.
Ora vedevo. Ok.
Ok.
E se proviamo a cambiare pagina mettendo sul PowerPoint? Guarda qua. Ora vedi?
No, è condivisa. E non la condividi, cioè non, la devi condividere così.
Proviamo a condividerla così. Compatire. E adesso? Cosa vede? Si vede la sala?
Sì, dice che uno dei nomi era diretta, che dice che torna Valentino e
Ok?
ora c'è la diretta.
Ok.
No, mi sono che proprio
Ok, ora?
Ora questo.
solo la prima.
E se proviamo a togliere... E se proviamo a togliere la modalità presentazione? Vedi, prova a scorrere così le slide.
Così si vedono.
Non è normale.
Col PDF.
Col
E non ce
PDF.
l'ho.
Lo vogliamo fare un attimo?
Come si fa?
Salva, no, archivio penso, esportar, sì, qui, clicca, crea Adobe PDF, qui. Ok, prova a salvarlo così.
Dov'è la...
Penso che sia scrittorio il download. La
Sì, il desktop.
Il desktop.
Guarda.
Guardar.
Oh, che tu... vieni qua, che è tutto in spagnolo.
Sì, comunque loro ora vedono che stiamo parlando di PDF.
Perfetto. Ok.
Ok, se vedete se ora vedono sì? Ok, sì.
Allora, dove l'abbiamo?
PDF.
Eccolo qua.
Adobe. No, questo qua di sotto.
No.
Però vediamo se funziona anche così. Sì. Ok. Vedono il PDF?
No, non l'ho condiviso, scusa.
Ah.
Lo devo condividere.
Non appare.
È tutta la pantalla, compatire.
Prova a prendere adesso il PDF.
Andiamo.
Questo qua.
Vedi?
Sì, ma
Vedi una roba bianca, tutto bianco. Però può darsi che ci vuole un po' di tempo.
Per caricarlo.
non è possibile. E la scala.
A caricare tutto lo schermo. A cosa diventava? Fare tutta la pantaglia.
Ma non
va?
lo vedeva, no. Non lo vedeva. Se cioè non vedono adesso? Non si vede?
Infatti un test avremmo potuto farlo tranquillamente col nostro PC. C'è bisogno di aspettare gli altri.
Prova a tagliarti compatire. Ok, prova ad andare di nuovo qui su Jitsi. Proviamo a ricondividere lo schermo. Ventana.
Ma così ti
Se in modalità non presentazione la vedono, si vede?
Però vediamo così.
Solo la prima?
Prova a fare tutto.
Lo so, ma non vedo, c'è un misto di spagnolo e di roba varia. No?
È un problema di magari
Lei c'ha il suo PC, e se si connette al suo PC?
si potrebbe
Che se
fare,
esame
solo
solamente
che
la primera-
dipende dall'alimentatore.
Solamente la primera.
Perché se
Ecco,
l'alimentatore
ecco,
ha
tanto
3
c'è
spie
questa
non
primera.
si può collegare da nessuna parte. Io ho problemi
We
col
can
mio
try to share the whole
Hai
screen
l'adattatore?
instead of.
Ok.
Sorry. I've been required. No.
Cioè, stiamo ancora, che ancora non ho cominciato.
Share.
Non si vede fuori.
Prova.
Lo vedete?
It's okay.
Lo
Ok.
schermo intero, però anche io prima avevo messo lo schermo e non andava.
Ok. Thank you. Sorry for this inconvenience. Ok. Ok. Open questions. We are used to process multispectral data. Satellite sensors usually provide multispectral data, but at the same time, the most widespread UAV data are acquired by means of RGB camera. The objective of this research was therefore to analyze the performance of two pixel-based classification procedure that could be translated into an automated and easy to apply method, especially for end users with limited knowledge of spatial data processing. And so we asked, it is possible to perform a reliable land use land cover classification using high spatial resolution, RGB bands, and how does spatial resolution affect the performance of pixel-based classification algorithms? And the objectives, there are three kinds of objectives: to analyze the performance of supervised and unsupervised classification algorithms using orthomosaic generated from RGB images from UAV, and at the same time to test whether vegetation indices based on visible bands could improve the performance of classification algorithms, and finally to analyze possible relationship between the performance of classification algorithms and the spatial resolution of RGB UAV imagery. In this work, we identify two study area, an extra-urban environment near Matera, Grottole, in the province of Matera in Italy. And in this scenario, as you can see, high vegetation and bare ground soil and a viaduct visible was emerged in this slide, in this figure. And so we used the DJI Mavic 2 zoom as UAV instrumentation with equipment RGB, F4, etc. I am not in this moment to continue with to identify the correct instrumentation. You can read easily. In the second study area, We worked in in an area called Punta Penna near Bari, because the promontory over the sea on which it stands is an important archaeological area. Unlike the first case, the presence of water is assessed in this scenario. And we used another typology of DJI Inspire 1 version 2. And for the first data set, a GNSS acquisition campaign on 11 ground control points was carried out and measured in NRTK mode with an average accuracy of 2 centimeters, considering the 3 axes, and in order to perform an indirect georeferences of the photogrammetric products. For the second case, directing georeferencing was preferred, and using image geotags measured with a low performance GNSS receiver with an average accuracy of 3 meters. The survey strategies where the first one, as you have understood, different UAV sensor and cameras, and different georeferencing strategies, and different above ground level altitude. The 4 different ground sample distance were retrieved. And for this aim, 4 orthomosaics were exported for each scenario examined. As you can see in the table, we begin with the highest resolution, and then doubling, tripling, and quadrupling the former. The methodology at this point, 4 orthomosaics were exported for each scenario investigated, and the orthomosaics were imported in the open source QGIS software. And as you can see, following the procedure, we, as a first step, we adopted the empirical line method to produce a radiometric calibration of data, and we tested the results on various land cover, the test vegetation, asphalt, and bare soil. Several vegetation index based on RGB bands were evaluating, and then performance was analyzed in terms of the ability of distinguish between vegetative and non-vegetative classes. The most robust in terms of performance were the triangular greenness index and the red-green ratio index. The TGI and the IRG indices were exported from QGIS software and uploaded in the open source Sentinel application platform or SNAP provided by Copernicus Systems. And the aim of this operation was to have the possibility to, in the future studies, to integrate, to compare with other kind of satellite data, and we had the possibility to test also the importing external data in this software, in this platform. SNAP provides several supervised and unsupervised raster image classification algorithms, as you can see. For this test, the processing chain concerning classification with supervised random forest and unsupervised Kappa-Mint clustering algorithms were adopted, and the supervised random forest system, as regards the supervised classification, we we determined 10 area of interest per class to attempt to collect within them the spectral variability and texture of each class, and the methodology used to create a training data set for the automatic methods guarantees that the training data always cover the same percentage of area for each class, which assures the usability and robustness of the algorithm. As regards the unsupervised classification, the Kappa-Mean algorithm has the advantage to be quite fast, as few calculations and consequently little computer processing time is required to calculate the distance between the data, the centroid of each at each iteration. But there are some drawback. Firstly, is necessary to select how many K group to show. This is not always trivial, as it is not always possible to do this, especially for problems of higher complexity. In addition, this algorithm also starts with a random choice of centroids and therefore may produce different clustering results on different sequences of algorithm. In the snapshot software, the unsupervised algorithm, we choose some parameters. For example, the number of cluster was set to 5 and the default number of iteration to 30. At the end of this of each processing, the clusters generating were manually labeled according to the class to which they could be identified. In this figure, you can observe the results in supervised and unsupervised classifications from qualitative point of view. And at each resolution, we considered the result for each kind of resolution. And a qualitative inspection, this is the first scenario, this is the second scenario. A qualitative inspection comparing the corresponding classification reveals the difficulties of the K-means algorithm in comparison to random forest classification. If on the one end the identification of vegetation background are quite reliable in the unsupervised classification, instead the difficulty in the distinguishing, for example, asphalt from other classes and vice versa. The same algorithms exhibit the same problems in the second study areas. And in fact, the most critical issues are found in the clustering of water, which is often included in other classes. These are the confusion matrix metric, and we use different kind of validation metrics, and we can conclude, as hypothesized, the supervised random forest classification give us very affordable metrics, and in general 13% reduction in the value of the analyzed method was found in the latter classification. And especially for the unsupervised classifications, the presence of vegetative index, vegetation index, improves their algorithm the separation capability. And it's clear that it's preferable to use bands in the near infrared for a better automatic extraction of the vegetation. And we notice that there is no regularity between the separation capability of the classification algorithms and the spatial resolution. The efficiency is very much influenced by the context and any similarities between the reflectances of the various classes, for example, vegetation, water, or background, and asphalt. And we can see that the reduced resolution compared to the original one optimize the classification times and capability, and at the same time there is the reduction of noise in the image. Thank you for your attention and for having waited me for this presentation. I think it's better to go on with because we need to test also the system and at the end of session we can make some question. Okay, it's late probably because we need to continue with the next session. Guarda, c'è il virtual.
Well, we can try. Can someone say something?
Okay, sì.
Yes.
We can move with on the next speaker.
Yes.
The next speaker is Federica. Are you here?
Yes. Good morning.
Okay. Federica Ghilardi comes from University of Turin.
Yes.
And she worked together with Samuele De Petris, Alessandro Farbo, Filippo Sarvia, and Enrico Borgogno Mondino. And is presenting the paper, the work exploring stability of crops in agricultural landscape through GIS tools and open data.
Yes,
Federica,
good morning. Yes, good morning, everyone.
You can start.
You can hear me?
Yes.
Yes, thank you.
Okay.
Good morning to everyone. I'm Federica Ghilardi, a PhD student at University of Turin, and today I'm presenting our work. Okay. Extreme events are causing important damage all over the world more and more frequently. And of course, agriculture area could be involved and damaged, for example, from flood event. Therefore, an accurate damage assessment is essential for flood planning, restoration, and prevention action. To estimate flood damage caused to agricultural area, many models have been developed, but most of them consider the crop as stable in terms of type and position over the year, not considering one of the most important agronomical practice related to crop rotation. In fact, crop rotation is an agronomic practice that consists in planting a sequence of different type of crop on the same field and also permits to control environmental stress and crop performance. In a context where climate change lead to an intensification of weather events, the study of crop type assessment is crucial for the estimation of the potential damage from hazardous event. So, the study of crop stability is a central element since conditioning reliability of long-term prediction about potential flood damage. So, we have two important questions to give an answer. Can the local agronomical landscape be considered invariant a long time? And if the answer is no, what is the frequencies and the size of this change? So the work was based on a change detection approach and on the use of free data obtainable from open archives. The employed material are in particular cadastral map and the farmer cap declaration about early crop type. And the performance analysis are the early crop spatial distribution, and we want also map and quantify crop change a long time. Speaking about the study area, An agricultural area located in Piemonte region was selected as area of interest. And this is particular area because agriculture represents one of the most important economic resources. This area size more than 16,000 hectares, and it's characterized by the presence of Po River, one of the most important Italian river. It's well known that this river is floodable, so represents a high risk for the surrounding crop. So speaking about the available data, we use in particular cadastral map and crop type declaration. About the cadastral map, this data is available for free within the BD3, the Territorial Reference Database for the regional institution of the Piemonte region, and this is downloadable from Piemonte Regional Geoportal. This type of data is available as polygon vector layer shapefile, and the update is in 2020. So this data give information about the parcel geometry, but do not give information about the associated land use. In particular, in this work, more than 20,000 parcel was considered. So to qualify parcel in terms of crop type, the CIAP, so the Piemonte Agriculture Information System database, was used to obtain the crop type information through the agriculture register. This type of data is available as a table format, .csv, and the update is every year. So we have data from 2015 to 2020. In particular, this type of data give information about the main crop type cultivated at parcel level, but not give information about intra-annual rotation. Sometimes happen that parcel can be split in multiple sub-parcel, and sometimes we have with this data information about the main crop type cultivated on it. This is important for the following analysis. In this work, we use all the available data, so we use a reference period from 2015 to 2020. So to map the crop type, we use this input data. Both the cadastral map attribute table and the external one from agriculture register contain a separate code about the municipality code, cadastral sheet code, and cadastral parcel code. To assign the crop type information to the correspondent parcel, an identification code was generated with GSI tool and involving the string and number. So the code was computed for the external table from agriculture register and for the cadastral map. But attention, as we saw and as we see, agriculture register sometimes report information about the sub-parcel level. So in this point at the process, to assign to the single parcel has been assigned the crop having the biggest declared area by the farmer and recorded in agriculture register. So the results is for each year a map of early crop type and at parcel level. We focused our attention on 8 different crop type, as you can see in a legend. So there are other composed by greenhouse, minor crop, horticulture, and so on. Rice, soya, corn, meadow, wheat, barley, and arboriculture. So you can see the results in this slide. So we have one map about crop type for each year, and the graph, as you can see now, for maybe try and show the results more in detail. So we can see that rice and corn are the most cultivated crop in area of interest, with more than 4,000 hectares and 2,000 hectares, respectively. The soya and the barley are the least one. And observing trends, we can see that meadow, barley, and arboriculture has an increasing trend during the reference period. Instead, wheat as a decreasing one. During the reference period, we can see also that rice and soya fluctuated, and other crop and corn remain stable. So, to assess temporal crop variability, the following conditions were tested at parcel level 2 years in 2 years. So, if the parcel changed crop for 2 consecutive years, the parcel was coded as unchanged. So, UC. If the parcel change crop between 2 consecutive years, for example, 2015 and 2016, is change the crop, the parcel was coded as changed crop, so CC. You can see the results in a table. So we have the ID code for the identification of the parcel, area field that give information about the size and the dimension of the parcel, and you can see the UC and the unchanged crop and changed crop code. This is important for the estimation of early change in terms of ethers, affecting the corresponding crop type. In this slide, you can see the results more in detail. Regarding unchanged crop, we can observe that other crop, rice, corn, meadow, and arboriculture are the most stable over the time. And these results is coherent to the local agricultural context. It's well known that rice tends to be cultivated on the same field for many years, and similar behavior affects arboriculture. For example, a new plantation of vineyard are expected to be maintained for 10, 20 years. Otherwise, we can see that soya, barley, and wheat resulted the most bearing one. And this is coherent with the local agrocultural, because this type of crop are the main crop related to crop rotation. Regarding changed crop, we can see that in 2016, there is an increase in rice declaration, and it is symmetrical to the decrease in the same year. This, we think that this outcome is due to the early transitional phase in agricultural register, being 2015, the first year of acquisition. Also, we can see that during the following year, we can see that there is a migration from other class declaration to a specific one. Another important things that we can observe is the trends of soya and wheat crop. It's curious that one go down, the other go up, and it's typical of crop rotation practice. So, concerning crop type transition between 2 consecutive years, CC, so changed crop, was used to compute the total area that moved from one class to another. So the parcel was coded as L for decreasing value, so lost, and was coded as gained, so G, for increasing value. In the graph, we can see that corn, wheat, and soya are the most variable classes, and these results is coherent with the local agronomical management. Otherwise, we can see that meadow and arboriculture show the smallest transition, and if we observe, we have G value. We can observe that G value are biggest than L value. This suggests an increase in terms of area for these two classes over time and during the reference period. Okay. CC value also was used to count parcel level change during the reference period, making possible to summarize the local degree of variability. Crop variability was mapped in crop variability map, and the cumulative frequency distribution was computed. We can see that 45% of parcel not change crop during the reference period. These parcels are located in the north of the area of interest, where the dominant crop is the rice. And we see that the rice is stable during the time. Otherwise, only less than 10% of parcel change crop every year. And we see that in this parcel are characterized by the cultivation of wheat and soya, involved and related to crop rotation. So summarizing, we started the presentation with question. Many models consider the local crop as stable in terms of position over the year. We demonstrate that in this area this not happened. So rice, meadow, and arboriculture are the most stable, and corn, soya, and wheat has a primary role in crop rotation. We also develop crop variability map, highlighting the most timing varying zone, and we also develop operational tool useful to help damage assessment in for agricultural sector. Future development, we want to expand the study to the entire Piemonte region. We want to analyze a crop like other and arboriculture in detail, and we also want to develop crop probability model to have an estimation or a percentage of probability to find a particular crop in a specific parcel, taking account the historical references. So thank you for your attention, and I'm finished.
We cannot hear Eufemia.
Thank you.
Thank you, Federica, for your interesting presentation. Before moving to the next speaker, I would like to ask the attendees if they have any questions. We can move to the next presentation, to the next speaker, Alessandra Capolupo, with Cristina Monterisi, Danilo Spasiano, Alberto Ferraro, Matilda Mali, and Roberto Fratino. She is presenting, they comes from Polytechnic University of Bari, and she is presenting the paper, a WebGIS prototype for visualizing and monitoring the spatial temporal change in seawater quality. Secondo? Il primo? Ok.
Cliccaci sopra però.
Comparire.
Ok. Dovrebbe andare. Ok. Prova a presentare.
Okay, are you seeing the screen?
Controllate.
Yeah, okay. I think that maybe no one answered, so I think that maybe they are seeing. So, good morning, everyone. I'm Alessandra Capolupo, an assistant professor at the Politecnico di Bari. And today I'm going to introduce to you the prototype that we developed at the Politecnico di Bari for assessing and monitoring at the same time the changes in seawater quality. That because the eutrophication phenomenon is currently recognized as one of the most critical environmental issues. Indeed, it is mainly due to the human pressure and in particular to the growth of the population near to the coastal areas. These triggered the deterioration of the coastal environmental systems, both in terms of goods and services. And for that reason, the European community issued a various European directive in order to monitor the situation, but also to try to preserve these kinds of environments. And at the same time, the scientific community communities, he is developing a lot of fact-finding tools that are devoted to monitor and at the same time also to assess the water quality situation. For sure, among the different components that could be developed, the geographical information system played a crucial role, since they give us the possibility to also to visualize, but also at the same time to handle heavy geospatial data. But thanks to the advancement in the technology and to internet coming, the web application replaced the GIS information, and so the web GIS boards. So which are these GIS elements? Actually are some platform, usually based on a 3-tier configuration that gives the user the possibility to visualize and at the same time to interact with the data that are uploaded on it. So for that reason, usually in order to also to allow to everyone to can access to them, the free open source software are used and to implement each single module of each single layer in compliance to the ISPIRE directive. So which is the main aim of this presentation, of this work? For sure, we want to introduce our prototype, and at the same time, we want to underline the potentiality of this system to different kinds of users, as well as local, national, or European consumer, as well as also scientific community. In order to identify the optimal eco-compatible management strategies that give us the possibility to preserve this fragile ecosystem. In particular, after detecting the potential user and collecting the feedback, all the open data sets, available data sets were investigating in order to understand which data could be detected and could be collected, and which one instead should be acquired through on proper field data campaign. Thus, after that, a good, proper WebGIS application was designed in order to respect these kinds of, to implement, to upload all this data, but also to respect the requirements of the user. And so when their capability was defined, this system was implemented, and after his performance was evaluated. Indeed, this WebGIS application was based on the workflow that was suggested by Uxold and Lenson, that is characterized by 7 main steps. First of all, it is based on the definition of the problem that we want to assess, and on the definition of the potential user, both skilled and not skilled potential user. After that, all the requirements of the user are investigated, and on this feedback, the feature of the systems is defined, and also is defined as well the capability of the prototype system. So it is designed, and finally just the prototype is implemented to see if the prototype is working well. Its performance was evaluated, and only when their performance is satisfying, it was really implemented a real platform, and the final performance was evaluated too. Actually, in this moment, we have just implemented the prototype, and we evaluated this performance that appears promising. So after defining all the requirements and the features that are needed to define the WebGIS architecture, WebGIS system in total, this architecture was defined, and all the data that are needed to explain and to monitor the problem were defined. So for that reason, the main open data sources were investigated, as well as the national national geoportal, as well also the SIT Puglia and ISPRA dataset. just for the data that are not that were not available. Some field campaigns were properly planned in Puglia region, and on the base of the data that were implemented, an intuitive and interactive interface was constructed, and such data were implemented on it, were in proper drop-down menu, and finally they can be visualized and analyzed by the user. Such platform was implemented on the Puglia region, and in particular were selected 5 main ports: Bari, Mola, Monopoli, Lecce, and the last one was Santa Maria di Leuca. And on the base of these results, on the base of the field, why was chosen for sure these ports? Just because Puglia region is characterized by a really complex coastal morphology, because it's showing a various typology of morphology. So it's really complex to define and to monitor it, the sea water quality. So for that reason, it was chosen as the object of our study, but also because this prototype has also the aim to disseminate the results of a SMART project, which is a project funded by Puglia region. So, as already shown as suggested by the literature, a 3-tier configuration was selected, was picked up, and in particular, it was organized by a presentation tier that is characterized by the web browser, by the web page that that allows user to access the data and also to interact with the platform, and to query also the data. After user query the system, such question is transmitted to the map server and to the geo server as well, in order to interact with the geo database, but also to handle the data within the geo database. And to perform this kind of application was designed a proper layer, the application tier, that is actually devoted to handle the geospatial data, actual geospatial data. Of course, all this system was correlated by some additional and external data that gives the possibility to introduce the base maps like the Google Maps or the Bing Maps, but also by PostGIS and by PostGIS that gives the possibility to import also the external data file like in VuFM or VuSM, VuCM format within the system. So what was the result of this prototype? You are seeing in this slide the interactive interface. As you can see on the right, there is the viewer window. Then the map are visualized, and where are visualized all the layers that are activated. It says on the left, you can choose the different layer that you want to visualize. On the top, you can see just the base maps. It says on the top of this layer, you can just see all the data that are implemented within the platform, that are organized in round up menu. And of course, each layer was implemented in the correct menu, because each menu gathers together data that provides similar information. Just on the bottom of on the bottom left, you can see the possibility to download the data that you are visualizing, and you can also define and select the format that you prefer during the download. It says in the map window, you can also see some navigation tools that help you to navigate within the map. So, for example, you can zoom in or zoom out, or you can read the coordinates of the point that you are visualized. For each single dataset that is implemented in the platform, you can analyze, you can investigate the coordinates, so you can have the information about the registry of your station, or you can see the metadata of your layer, or you can also see the data that are corresponding to that point in terms, of course, of seawater quality, but also air quality, sea temperature, so all the elements that could be important and relevant to monitor the information of the seawater quality in Puglia region. For example, here you are just see the hydrocarbon features. So for sure, the WebGIS application appears as the optimal tool to widespread the results of iSmart project, but also in general to widespread the geospatial information, because it allows to gather together information that are concerning the same environmental issue. It is organized by an intuitive interface, so both skilled and not skilled user can access the data, but also handle with it, visualize them, and also define, just visualize and interact with the data that they are interested in. And also most of the data that are implemented are actually the time series, and this gives the possibility to monitor the sea and air quality over the time, and so to see also and to see the real changes that are suffering this parameter over the time. Which are the limitations of the limits actually of this system? For sure, it is just a prototype, but visualizing and investigating its performance, we can see that they are in time, they are in line with the literature in terms of the processing time and in the time that is needed to query the system, but at the same time we have a little bit difficulties to manage a lot of simultation users that want to interact with the platform. So in the future we want to, for sure, try to improve this aspect of the system. So thanks for your attention.
Thank you, Alessandra, for your presentation. Does anyone have any question? We are quite late, and it's better to continue to move on to the last presentation for this first session of GIRM. Alberico Sonnessa is here. Okay.
Yes, can you hear me?
Yeah.
Okay.
Alberico. Okay. Okay. Alberico Sonnessa and Mariano Macellari wrote the paper Dynamic Monitoring on Railway Steel Bridge with the MEMS as accelerometers. First results on the case study of Portella. Alberico?
Yes, I'm sharing my screen. Can you see it?
Okay. Yeah.
Okay. Good morning to everyone. Sorry, I've got a bit flu, so my voice is not very clear. But anyway, let's go on. I'm Alberico. I'm from the Polytechnic University of Bari, and I'm going to present this work that is called Dynamic Monitoring of a Railway Steel Bridge with MEMS accelerometers, first results on the case study of Portella. As usual, let me thank my co-author Mariano Macellari, that is now currently working at Trenitalia, one of the biggest players in the field of railway transportation in Italy. And let's start with a consideration. There is now a big and increasing demand for mobility, as witnessed by the expansion of the TEN-T European transport network that is the roads, railways, and airport infrastructure under development currently in the European Union. Okay, there is an increasing demand for mobility, but there is also an increased demand for fast and green mobility. Okay, that's why high-speed railways are very, very important and are becoming always more and more important. In the last 20 years, we went from 2.5 thousand kilometers to about 10,000 kilometers of railway tracks here in Europe, high-speed tracks. Of course, an increasing demand for mobility needs a demand for, let's say, monitoring, because all the infrastructure is under a load that is always increasing. Especially rail bridges can work close to their operating limit in terms of number of train load frequency. So this can speed up their deterioration process. That's why there is an increasing demand for monitoring, and the monitoring the infrastructure and especially a railway bridge during the entire life cycle of the structure is, let's say, we can say, it's a new way of thinking. It's the need now is monitor an infrastructure from the start, from the beginning to the end. Okay, in order to avoid, of course, critical events such as deformation or collapses. We all, of course, remember the Morandi Bridge. Let me present our case study. The Portella Bridge. The Portella Bridge is a steel bridge located on the Roma-Formia-Napoli railway. It has a span of 28 meters and is composed by two reticular beams with longitudinally at a distance of 10 meters, about 10 meters. And is designed for allowing a maximum operative speed of 2,000 kilometers per hour. This bridge has been equipped with 10 3-axis microelectronics system as accelerometers, MEMS accelerometers. Their frequency range response is from 0 to 100 Hertz, more or less. They sample the data at 200 Hertz. And how we record the data? Two triggers are posed on the two tracks at the end of each tracks, the even and the other tracks, and automatically detect the train approach and give the start to the beginning of the registration. Okay, so we have a registration for each train passage. Which is the aim of this monitoring system? Is detect natural vibration frequencies of the steel structure. But the question is this system reliable? Let's say some data. Let's analyze some data. Let's start from accelerations. I repeat, the main aim is to detect the natural vibration frequencies. But to do this, we need acceleration. We performed this analysis on 3 weeks, characterized by different weather condition, let's say pressure, temperature, and so on. Week 1, called W1, from 28th of April to 4th of May. Week 2, from 28th of July to the 3rd of August. And week 3, from 27th of October to the 7th of November. Okay, this is a synoptic view of the maximum acceleration suffered by the bridge during these weeks. And what we can say is, okay, this is a table where I reported just the maximum acceleration suffered by the bridge for every axis, X, Y, and Z. let's take insight on these results. On the x-axis, sorry, the maximum and minimum acceleration are about 21 meters per second square, more or less. On the y-axis, the maximum acceleration is around 24. On the z-axis, the minimum acceleration is around 33. The maximum acceleration is around 40 plus g. Let's say I'm going to explain this data. We have to take a look at the graphs, at the accelerogram. Why? Because I told you that on the y-axis, the maximum acceleration was around 24. But looking at the graphs, this is not the real maximum acceleration, but we reach the maximum acceleration detectable from this instrument. So there is a weakness in the monitoring system. Okay, we can really say that this is the maximum acceleration. But take a look at the second graph on the z-axis. For the maximum acceleration is around 40 meters per second square plus g. Why plus g? Because here the scale is different. We start measuring from g, from the gravity acceleration. Okay, so on the z-axis we have the opportunity to have a major range of measurement. Okay, so the real acceleration 33, this one, the peak acceleration measured on the z-axis that is expected to be the maximum acceleration on this direction, can be taken as indicative of the maximum acceleration of the bridge. So we can say that this value is the real maximum acceleration of the bridge, around 34 meters per second square, per square second. This is analysis. This is this is an average, synoptic view of the average acceleration, the weekly average acceleration. What we can say is that the maximum acceleration is detected on the y-axis. Okay. So first results for this part is that on the 3 different weeks there are no difference due to the weather. Okay, so the system, the bridge doesn't answer in a different way depending from the weather. And on the epsilon, on the y direction, we found the maximum average acceleration. But let's move on the most important part of the work. Okay, so the analysis of the vibration normal modes. So to find to assess the vibration normal mode, the natural frequencies of the bridge, we used fast Fourier transform, an FFT, code developed on purpose, in order to go from the time domain acceleration in time, to the frequency domain. Okay, how we performed this this analysis. The train triggered the acceleration by passing on the bridge. The bridge starts oscillating, accelerates, reaches its maximum, and then starts to fade the acceleration. On the tail of the signal, we performed an FFT in order to retrieve the frequency, the natural frequency of the bridge. So let's move to the results. This is we performed this analysis only on 6 accelerometers, because the 4 accelerometers on the bridge, on the shoulder bridge, didn't provide enough power. Okay, because they are stable. So, on the 6 accelerometers on the span of the bridge, we calculate median, median, and standard deviation of the first natural frequency detected. Results. The bridge behavior appears to be homogeneous both in transversal and longitudinal direction. The detected frequencies are around 15 Hz for the X and Z axis, and around 34 Hz for the Y component. But the standard deviation is a bit higher. It's around 15-20 Hz in all cases. Some consideration on the system. So, natural frequency detected, of course, by the system are around 15 plus 20 Hz for all components, which was the starting frequencies used in the design of the bridge. So results have been compared with the outputs obtained from the finite element modeling of the bridge. Results are a bit weird, I have to say, because the natural frequencies used, so the design natural frequencies was from ranging from 5 to 10 Hz, one order of magnitude smaller than the experimental frequency. Why is big discrepancies between the experimental and the design natural frequency? The first hypothesis indicates the underestimation of the action of some structural constraints as possible cause. However, we cannot exclude the malfunctioning of the shield against electric power, the parasitic currents, because the train, every passage of the train produces parasitic currents. If the system is not set up correctly, the system measures frequencies, current frequencies, and not natural frequencies of the steel bridge. So we have to go into deeper into this issue. Some remarks about this system. For sure, the system based on accelerometers is an effective and low-cost tool for monitoring bridge with some few euros. You can have an affordable and reliable monitoring systems. But the system provides reliable results under the condition that a careful setup is made, comprising a startup period to analyze possible external interferences, for example, parasitic current. And plus, this system is easily upgradable with additional sensors, for example, low-cost GNSS, for strengthening and integrating the output parameters useful for the structure manager. Thank you very much for the attention. And finally, please let me say happy birthday to our chair, Eufemia Tarantino.
Thank you, Alberico. We have, if there are any questions for this presentation. Okay, we have just concluded this workshop, and I invite all the attendees to participate to the next section scheduled for this day. See you later.
Bye.
Bye. Thank you.
Thank you.
Bye.
Bye.
Can you hear me?
Yes. Sì, sì,
Okay, okay, okay. Good morning, everybody. We can start this second workshop named Geomatic for Resource Monitoring and Management. We can move with the first. I'm Eufemia Tarantino from Politecnico di Bari, and I am the chair of this section. I can move. We can move with the first speaker, Giacomo Caporusso. Giacomo and Marino Dell'Olio and me, Eufemia Tarantino. We worked on. And we wrote a paper. Use of the Sentinel-1 satellite data in the SNET platform and the web GNOME simulation model for change detection analysis on the Persian Gulf oil spill. You can start, Giacomo. Okay. You need to share your presentation. No, not. You need to share it inside Jitsi,
Okay.
inside the platform.
This?
Yes, but okay. La ventana?
No, clicca sul monitor.
No.
Perfetto, compati.
Compati?
Poi scegli la presentazione.
Okay. You can go. Okay.
Okay, and then
Thank you.
thank you. Can you see my presentation here?
Yes.
Okay. Okay, good morning to everyone. I am the PhD student Giacomo Caporusso, and I am going to discuss the research work carried out by myself, Professor Eufemia Tarantino, and Marino Dell'Olio. The goal is to analyze the oil spill that occurred during the accident by coast in March 2017. The data are SAR images provided by ESA Sentinel-1 mission. The instruments are Snap desktop platform provided by ESA and WebGNOME, a web application developed by the National Oceanic and Atmospheric Administration. The methodology involves a SAR change detection and at a later time the creation of a dynamic oil propagation model. Okay. The work initially involved the acquisition of satellite images which were later pre-processed. Afterwards, coherence estimation operations, change detection operations, and application of oil spill tool integrated in SNAP were performed, the results of which were then compared with each other. A dynamic model was used that made it possible to obtain an image later compared with that obtained by change detection and a numerical analysis using the ADIOS tool. The satellite images used are those acquired by Alaska Satellite Facility Data Search on February 12 for the pre-event and the images of March 8 and March 11 for the post-event. It was decided to use SLC images in addition to the more usual GRD because the latter received a different pre-processing with unknown parameters that can, in some cases, distort the measurements. Through SNAP, it was possible to carry out a series of pre-processing in order to make the images suitable for subsequent operations. In particular, the orbit file was applied, calibration, thermal noise reduction, debursting, multilooking, speckle reduction, ellipsoid correction, length in mask, and finally a conversion of the backscatter value into decibel was performed. These are the effects of the preprocessing operation on an SLC image and on GRD image. The result to obtain in co-registration is to spatially align the two images so that the characteristics master images are superimposed on those of the slave image, to which the first is copied to be able to make a comparison as accurate as possible. In some of the previous elaborations, the problem of video noise emerged, something common in the field of remote sensing. By smoothing, we reduce the high frequencies details. The backscatter value of each pixel is defined according to mathematical relationship with those of the backscatter of the pixels surrounding it within a kernel of a fixed size. Among the various mathematical filtering relationship, the choice fell on the median blurring, which averages all the pixels belonging to the same kernel and replaces the values of all pixels with the one calculated in the kernel. This filter was used exclusively on the image depicting the pre-event to further reduce the salt and pepper noise caused by irregularity of the sea surface. In our work, the effects of kernels of 10 for 10 and 20 for 20 sides were evaluated. For the determination of the threshold value, first of all, two sections were traced through which a water oil discriminant value equal to minus 25 decibel was calculated. Subsequently, 4 sections were drawn that crossed both water and oil. The values above and below minus 25 decibel were separated. A difference was made between the mean values of the speckled pixel before and after the event, obtaining 4 threshold values, the average of which resulted in the optimal threshold value. To perform the calculation operation between the two images, the band math operator was used, by means of which a subtraction was made between the backscatter values of the master image and those of the slave image. Subsequently, a binary mask was created, composed exclusively of pixels having a threshold equal or to or greater than the values we have chosen. This raster was exported and preprocessing using the QGIS software. Within the latter, a vectorization operation was carried out and the sieve classification was subsequently carried out using the semi-automatic classification plugin tool. Sieve classification is a procedure that allows you to replace the value of the isolated pixel with that of surrounding pixels. Finally, through the field calculator tool, a calculation of the total area occupied by the vector was carried out. These are the output of change detection for SLC and GRD images. Inside the Snap software, there is the oil spill detection tool based on an algorithm that can be used for detecting oil spills. The operator follows the following operations: a preprocessing phase in which a calibration, speckle filter, lens masking, dark spot detection, which dark spots are identified using the adaptive algorithm. Finally, a clustering and discrimination phase in which the identified pixels are collected in clusters or eliminated on the basis of the minimum size chosen for cluster information. This is the output of the oil spill detection tool. Coherence in interferometry is a measure of how much a pixel remains similar to itself over time relative to the phase parameter. Initially, the coherence values were analyzed using sections that crossed the oil stain. This methodology, due to the prevailing inconsistent nature of the sea within the sheen, did not yield useful results for the purposes of our research. Given this, later geometries were built externally and internally to the spot displayed in the reference image, and the differences between the average values of coherence calculated inside the spot and outside were measured. NEOM is a web-based software developed by NOAA, which allows you to generate a dynamic model of the spill and analyze the chemical, physical changes. The following input data have been entered into the model: the trend of the wind, the temperature and the salinity of the water, the trend of currents, and the characteristics of the spill. Subsequently, the calculation of the volumes spilled was carried out on the basis of the surface determined with the different procedures used, assuming a thickness of the oil equal to 1 micron. The results were compared with the value found in the literature. Through the threshold value determined by us, we obtain values that deviate from the comparison value by 5–6%, with the similar between the SLC and the GRD images. By means of the Snap Oil Spill tool, values are obtained which differ by 16%. In current estimation, a difference of 1.5% and 2.2% for the 19th percentile was detected between the stained pixels. The output data of NEOM model was exported to QGIS and compared with the obtained from satellite images, showing a good matching between the two. Finally, the ADIOS tool was used, included in the NEOM platform, which carries out a chemical physical analysis of the spill. Starting from the previously computed volume of floating oil, it was calculated that 401,000 gallons were spilled into the marine environment, and 230,000 gallons evaporated. 4,085 gallons were naturally dispersed, and 526 gallons settled. In conclusion, the study therefore demonstrated the greater efficiency of the change detection of two images compared to procedures that analyze a single image, the greater efficiency of a statistically defined threshold, the lack of appreciation of the results obtained for the coherence analysis, the usefulness of the WebNeom software as a validation tool for the analysis conducted with satellite images. Finally, the usefulness of the ADIOS tool for the reconstruction of the various components of oil spill. And for future developments, comparison between the results obtained by change detection of multispectral images with those of radar, comparison between results obtained by different radar satellites, and the use of NEOM software to predict the trend following the satellite survey of the spilled oil in order to calculate the timing and methods of environmental risk mitigation interventions. Thank you.
Thank you, Giacomo, for your interesting intervention. If the participant want to ask something to Giacomo, we can go on and with the second presentation. Giacomo with Cristian Gallo and me. We wrote this work, this paper, change detection analysis using Sentinel-1 satellite data with the SNAP and GE regarding oil spill in Venezuela. You can start with this second presentation.
Can you see my slide?
No, not this time.
No, devi fare prima. Prima. Devi andare. Ok. Jitsi, ok?
Ah, compatire, ok.
Compatire, ok.
Okay. And now?
Okay, now yes.
Okay, thank you. So, in this work, the goal is to analyze the oil spill that occurred during the accident of the Venezuela coast in July 2020. The data are synthetic aperture radar images provided by ICCSA, Sentinel-1 mission. The instruments are SNAP desktop platform provided by ICCSA, and the cloud-based geospatial analysis platform Google Earth Engine. The methodology involved in a star change detection. So, this is the workflow, and it consists in detection of oil surface in the marine environment through change detection of SAR images, image analysis through the Snap desktop platform, image analysis using an algorithm within the Google Earth Engine Cloud platform, determination of the optimal threshold for change detection in Snap and in Google Earth Engine, evaluation of the automatic methodology of ICCSA oil spill detection tool, and comparison of the results obtained from desktop and cloud platforms. The satellite images used for the case study were acquired free of charge through the Alaska Satellite Facility portal. The master image represents the scene closest to the event on the 31 of July 2020. The slave image is a scene in the absence of a spill, acquired on the 20th of February 2021. The images chosen for the study are SLC and GRD time, and this is the same reason of the previous presentation. Then, these are SLC and GRD master and slave images before the pre-processing steps. And these are the effects of the pre-processing operations on SLC master and slave images on and on GRD master and slave images. The result to obtain co-registration is to spatially align the two images so that the characteristics of a master image are superimposed on those of the slave image, to which the first is copied to be able to make a comparison as accurate as possible. In some of the previous elaborations, the problem of video noise emerged, something common in the field of remote sensing. By smoothing, we reduce the high frequency details. Among the various mathematical filtering relationship, the choice fell on the median blurring. This filter was used exclusively on the image depicting the pre-event to further reduce the salt and pepper noise caused by the irregularity of the sea surface. In our work, the effects of kernels of 5 for 5, 10 for 10, and 20 for 20 size were evaluated. Threshold values were statistically determined through a polygonal geometry within which only the petroleum pixels fall. This was certainly favored by the shape of the spot, which can be enclosed in a single geometry defined as a region of interest. In particular, both the average value and the 19th percentile were considered due to the presence of the same pixel characterized by anomalous backscatter values, the outliers. So, 4 threshold values were obtained and subsequently used in the change detection. To extract the dark area that represents the release of hydrocarbons, a difference is initially made between the VV band of the master image and the VV band of the slave image. Using the bandmax tool, the difference raster obtained is used to discriminate the oil pixels from the water pixels. This is done through the bandmax operator, in which an inequation is set between the raster difference VV and the various thresholds. Okay. Subsequently, to calculate the area relating to the oil spill, in each case, the oil pixels were counted using a mask. Inside the Snap software, there is the oil spill detection tool based on an algorithm that can use it for detecting oil spills. The operator follows the operations that I illustrate in the previously presentation. And okay, in Google Art Engine, the first operation involves in the uploading the Sentinel-1 image collection in the workspace. From the present collection, the availability of Sentinel-1 products exclusively for the GRD types is denoted. A rectangle was therefore drawn by inputting the coordinates of 4 vertices, which consists of the area of interest currently near El Palito, and the possibility to translate and modify in order to investigate other areas. Subsequently, the 2 products were selected through a series of Sentinel-1 image collection product filtering operation, type of VV copolarization, more effective than the VH in detecting oil spill, IW acquisition method, and descending orbit. Once the filters have been applied, the master and the slave images referring to the 31 of July 2020 and the 20 February of 2021 are obtained, each of which has been associated with a layer of the Google Art Engine main window. So in this slide, we can see the Google Art Engine layers of the master image and the slave image, both in black and white and false color composition. So the softening of the image aims to make the study area more homogeneous through a filtering of the height frequency pixel values. The computation process, which in Google Art Engine is called convolution, performs a linear combination of the neighboring pixels using a predefined set of weights. The results obtained are affected by the so-called edge effect, produced by the fact that approaching the border of the image, because the kernel applied to the pixel will not be totally occupied by other pixels that are part of the image. To overcome this drawback, it was decided to apply this operation to a geometry with an offset of 0.02 from the margin of the previously selected one in order to eliminate this effect. Okay. So, subsequently, comparison was made between the 2 radar images. The latter was processed by the math operators present on Google Art Engine, which allowed to obtain the difference image, determined precisely by the subtraction pixel by pixel of the backscatter values of the 2 images purchased in the same area of interest. The threshold value considered was obtained using the OTSU algorithm based on the analysis of variance between 2 classes, oil and water, of the single difference image. For a single band image with a bimodal distribution of the pixel, it is possible to perform a 2-class segmentation, finding a threshold that separates them. A bimodal image represents a plotting histogram of the backscatter values in 2 distinct distributions, almost separable from each other. The variance value between the classes is defined by the between sum of squares. So, based on the results obtained compared with the reference surface of about 260 square kilometer, detected on 26 of July 2020 by the Remote Sensing and Geospatial Analysis Laboratory of the USB, the proposed method found with successful oil surfaces. The best elaboration of SLC products in SNAP produce a percentage of difference of minus 1.13% from the reference value using a 19th percentile threshold value from the statistical analysis of the raster difference histogram with a smoothing filter with dimension of kernel equal to 545 and on the oil-free image. The best processing of GRD products is NEP produce a percentage difference of minus 0.85 from the reference values using a 19th percentile threshold value from the statistical analysis of the raster difference histogram and in the absence of smoothing filter on the oil-free image. The best results of GRD products in Google Art Engine produce a percentage difference of 6.67 from the reference value using the OTS threshold value and with a 3430 smoothing filter on the oil-free image. This slide shows the auto-print images obtained by Snap with SLC image, and this is for the GRD images. This is for the output of GRD images in Google Art Engine. And in conclusion, efficiencies of radar images for oil spill detection, improved change detection performance, improved efficiency of the 19th percentile and the OTS threshold, and poor accuracy derived from Snap's oil spill detection tool, and Google Art Engine greater versatility and speed than Snap. Thank you.
Thank you, Giacomo, for your kind presentation. Is there some question? Any question? Okay, I would like to ask you something, Giacomo, about the possibility to integrate the two methods for the study area. Do you think
yes, it is possible. It is possible, but only for GRD products, because Google Art Engine doesn't support SLC product.
Okay. Okay. Thank you. Thank you again. Okay. We can move to the next speaker. Mauro Palombella is here. Okay. Yeah.
Yes.
Okay. Mauro Palombella, Maria Francesca Bruno, Umberto Fratino, and Alessandro Reina. He wrote the paper Comparative Analysis of the Remotely Sensed Coastline with Geological Cartography, the case study of the Puglia region. You can start, Mauro.
Can you see PowerPoint?
No, you need to share. In basso.
Sì.
Ok. Stop sharing. Near the chat. Vicino alla videocamera, vedi giù in basso.
Sì, sì.
No, sono io. Are you able to share or left the meeting? Okay. To refresh, to enter is better for him. Fortunately, we have the time because we are in time in this session. Okay. Angela, if Angela Gorgoglione is in the meeting.
Yes, I'm here.
Okay, Angela. We can move to the next presentation. Angela Gorgoglione, together with Cosimo Russo, Andrea Gioia, Vito Jacobellis and Alberto Castro. They worked on the paper. They comes from Polytechnic University of Bari. And they worked on the name of the paper is the first flash occurrence prediction and ranking of its influential variable in urban watersheds, evaluation of XGB boost and shape technique. Angela, you can start with your presentation.
Hello, everyone. Can you hear me well and see my PowerPoint?
Can you see?
Mauro, we have just started with the following presentation. Please wait some minutes.
Okay. Thank you.
Angela, okay, you can continue.
Just let me know if you can see my presentation, only that.
Yeah, we can see that.
Okay, thank you very much. Thank you for your nice presentation. I introduce quickly myself. I am an assistant professor from Universidad de la República in Uruguay, South America. And I'm going to present today this work. Professor Tarantino already introduced it, already mentioned the title. This is a work in collaboration with researchers and professors from Politecnico di Milano and Politecnico di Bari. Just as a small introduction about the topic of the work that I'm going to present today. Well, since urban stormwater runoff causes, that is degrading the quality of surface water bodies, accurate prediction of water quality in urban areas plays a crucial role for minimizing stream pollution and also, I would add, protecting the health of aquatic ecosystems. So to this aim, during the last years, more and more scholars have been using data-driven models to complement the traditional physically based model that they have been using during all the time to solve these environmental problems. One of the most widespread algorithms in machine learning is ensemble learning. And in this work, we adopted one of these algorithms, specifically the extreme gradient boosting, the so-called XGBoost, since it employs the basic idea of gathering weak learners that are so-called decision trees to create a powerful model with a higher prediction rate. This why to enhance the robustness and the generalization ability by combining these multiple learners, a lot of these weak learners that we mentioned before. However, to our knowledge, XGBoost's ability to predict the occurrence of first flush in urban watershed was never investigated till now. And another aspect that we have to take into account in water quality modeling is the dynamic and random nature of urban runoff quality. Numerous studies have demonstrated that it is influenced by several variables, such as pollutant type, physical water quality characteristics, spatial and temporal factors that, they have to be taken into account to solve these kind of problems. However, only a few works have ranked such variables based on their level of importance in predicting first flush. Therefore, based on these considerations, this study aims to assess the XGBoost algorithm ability to predict the first flush occurrence in urban areas based on the 3080 first flush definition that in a couple of slides we are gonna define, and also identify and rank the input variables in terms of their importance in predicting first flush. This is the study area where the work is focused on. is a urban, essentially residential area, residential watershed located in southern Italy, in Puglia region, in the city of San Nicandro di Bari. Here we have some of the characteristics of the watershed. We have a drainage surface more or less equal to 30 hectares. It is covered by 70% of impervious surfaces, and it is characterized by a slope of 1.56%. Here we have a summary of the entire methodology that was adopted in this study. We can identify 4 main steps from these 4 colored blocks. The first one is represented by the dataset creation, here with the red block, and it includes a monitoring campaign, a precipitation generation model, here called IRP, that stands for Iterated Random Pools Model, a hydrologic, hydraulic, and water quality model, here called SWIM, that stands for Storm Water Management Model. And so we have a complete data set that is made of observations, generations, and simulations of 141 rainfall events. All this data set was then considered for this study. And the pollutants that were taken into account were total suspended solid, total phosphorus, and total nitrogen. The second step includes the data analysis, here identified with the blue block. This analysis was carried out with 2 main objectives. The first one was the application of the possibility first flash definition to the complete data set, or that's to the 141 rainfall events. In order to have the ground truth, then we used for the model, the application of the model. And the second objective, the second aim of this data analysis step was the discard, so identify and then discard possible correlated variables from further analysis. Afterwards, the third step presents the XGBoost classification model, here in green. This step includes also the cross-validation and the testing process of the model. The input-output matrix here is summarized in this parenthesis. This was considered for the model, and it takes into account as input variables the antecedent dry period, the precipitation average, I don't see my mouse, here, average and maximum intensity, the event duration, the total rainfall, and the runoff volume. While as output, output variables were considered the event mean load of the 3 pollutants that we took into account: total suspended solid, total nitrogen, and total phosphorus. After getting the best model, we said that this was tested, and for this cross-validation and testing process, we calculated the F1 score that we use as objective function, and also the accuracy of the model that was used more for validation, let's say. And once the best model was obtained, we performed the feature importance analysis, here highlighted in orange, by adopting a SHAP technique, that is a game theory method. Here there is the main concept on what this work was based. That is the 3080 first flash definition. In the literature, there are several definition and quantification of first flash phenomenon. This was the one that we adopted for this study. This definition says that an event a rainfall runoff event generates first flush for a particular pollutant when at least 80% of such pollutant load is washed off by the first 30% of the runoff volume. So here we have a typical representation of this definition. So this is a particular rainfall runoff event, and the pollutant that was taken into account for this event was total nitrogen. So we have the blue continuous line that represent the cumulative discharge for this particular event, and the red continuous line that represent the total nitrogen load washed off during this event. And then we have the red dotted line that represent the first 80% of total nitrogen load, and the blue dotted line that represent the 30% of the runoff volume. So because we have the 80% of total nitrogen washed off that occurred before the 30% of the runoff volume, we can say that based on this, on the 3080 first flush definition, this rainfall event generates first flush for total nitrogen. So, well, this was just an example, but this definition was then applied to the entire dataset for the 3 pollutants under study, and this information was then used as ground truth to train the XGBoost algorithm. Here we are summarizing some of the main results of the study. In particular, model performance. We can see here that we have 3 confusion matrices, 1 per pollutant. And it is important to highlight that both confusion matrices and numerical results that you can see here in the table, they are the result of the testing phase, of the testing step. So for the 3 pollutant matrices, for the 3 confusion matrices, sorry, we can see that the numbers on the main diagonal are the highest, and this is a good thing, it's a good result, because this means that the probability of predicting a first flush and non-first flush events as they actually are, well, for the 3 pollutant, total suspended solid and nutrients, is relatively high. And so in other words, this means that the model generates low false positives and low false negatives. From the numerical point of view, as I said before, as I mentioned before, we evaluated the F1 score that was used as objective function, and we also calculated the accuracy of the model. Both of them range between 0 and 1, so the closest to 1, the better the model performance. And here we can see actually that the performance of the XGBoost algorithm is very good. Here we are also showing the result of the feature importance analysis of the SHAP technique. The SHAP values were calculated for the input features, and the most important variables were ranked in terms of their degree of influence in predicting first flush occurrence. Overall, high values of all the input variables have a positive impact on the model outcomes, and here they are represented, as you can see in the legend, with the red color, while low values may not have any influence or have a negative impact on model results, and they are represented with dots with the blue color. In particular, it is possible to see that, first of all, there are 3 plots, 1 per pollutant, it was clear, and it is possible to see that the precipitation average intensity that we have here for TSS, here for total nitrogen, and here for total phosphorus, and also the event duration, D, and D, are always among the most important variables for the three pollutants, while runoff volume that we can see here, here, and here is always the least important variable in the prediction of first flash occurrence for both sediments and nutrients. So, based on such results, we can state that rainfall characteristics are more critical than the runoff characteristics in first flash occurrence prediction in urban areas. And this represents actually an advantage for machine learning models compared to the classical physically based models. In fact, the latter require not only rainfall runoff data, but also watershed characteristics, drainage network information, while machine learning models, well, XGBoost in this case, that is the model that we use, that we adopted, performs well only considering rainfall runoff input. And actually, based on the sharp results that we are seeing here, it may be possible that by reducing the input variables to only rainfall characteristics, its performance would continue being good even though a slight decrease may be detected. For concluding, well, we got more or less the main objective of the study. It assessed the ability of the XGBoost algorithm in predicting the occurrence of first flash in urban watersheds of the three most detected pollutants in urban runoff: total suspended solid, and the nutrients, total nitrogen and total phosphorus. And this was done based on the 3080 first flash definition. Here then I didn't summarize the main result because I have just mentioned and explained them. I just wanted to mention two important points that I believe are critical if we are working with this type of algorithm. Since algorithm and computing resources have been progressing rapidly, machine learning techniques are expected to be more often exploited in water quality studies, mostly when quick analysis and solutions are needed with a limited observation availability. However, the use of such techniques should be handled with extra care. This is important to take into account their limitations and constantly analyzing their results from the physical point of view. Thank you very much for your attention, and I'm glad to answer any question if there are. And I would like to say happy birthday to Eufemia.
Thank you, Angela. If the participants want to ask something to Angela, I would like only state about something about the testing of accuracy of your method, because it's similar to our in remote sensing image analysis, and finally yes, is similar to our point of view of using performance, accuracy performance.
Yes.
Thank you, Angela.
Thank you very much.
We can move if you, okay. Stop your sharing, please.
Yes.
Okay. And now we can move to the next speaker, Mauro. Okay. Okay. Are you? You can start. Okay.
Can you see now?
Mauro Palombella with Maria Francesca Bruno, Umberto Fratino, and Alessandro Aveina from Polytechnic University of Bari. They wrote this paper named Comparative Analysis of Remotely Sensed Coastline with the geological cartography, the case study of the Puglia region. Mauro, you can start with your presentation.
Thank you. Good morning.
But we are not seeing all your presentation. Probably you need to.
Allora,
no, la stiamo vedendo, però si vedeva un pezzo. Condividi il desktop, ok?
and now?
Help me.
Yes. You can start sharing your screen. This one.
Can you see?
Yes, I can see your screen.
I can start?
No, but we cannot see your screen.
Oh.
You have to click in the third button. In the bottom, yes. This one.
Can you see?
Yes.
Do you see the PowerPoint?
We see your presentation.
I can start?
In mode visualization, modalità diapositiva. No, allora, lascia questa modalità, vediamo le presentazioni. Ok, thank you.
Così va bene?
Ok.
Ok. Allora, good morning. As a research fellow, I collaborate with Maria Francesca Bruno, Umberto Frattino, and Alessandro Reina in the analysis carried out of the Polytechnic of Bari in the theme of the coastal erosion in Puglia. Among the other studies carried out, we have developed two themes in this work. We have analyzed the planimetric position of the coastline of the region of the Puglia region, using the 20,015 orthophotos made available by the State Property Office of the Puglia region. In this work, particular attention was paid to the geomorphological analysis of the coastline 20,015-7. In addition, in some stretches of the coast, coinciding with the gender sheet of cargo project, a comparative study was concluded between the coastline layer of the Italian official geological cartographic database and the coastline 20,015-7 digitalized. Paying close attention to the uniqueness of the data with the aim of the standardization the geological database managed by the region, the Puglia region, and the Italian Geologic Service. In in this week, the coastline was a generalized line leads back to INSPIRE's definition to shoreline or coastline. Particular attention was paid to the standard coding of the shoreline with clearly assigned attributes and codes. In this work, the coastline was digitalized when on video using the orthophotos as a basic. The analysis was carried out in this environment using the following layers. First, the new coastline digitalized, the layers of lithology classified by of the hydrogeomorphological map of Puglia, the coastline digitalized in geological sheet Ugento. And finally, the municipal, provincial, and regional ISTAT limits, 2020. In this slide, we can see the geological and cartographical framework. Structurally, the Puglia region is mainly included in the geological domain of foreland and in subordinaterally of in the geological domain foredepth. The geological consideration developed in this study originate from the hydrogeomorphological map produced by the region Apulia and considered a starting point of the other Apulian region territorial plans produced. The apparent simplicity and uniformity of the great morphogenetic regions that constitute it contrast extreme variability and complexity of numerous often interacting dynamic phenomena taking place, some capable of direct treatment. The geological structural setup is crucial to better understand the origin of the different types of coasts present in the area. In the next step, we show some type of coast localized in extreme and southern slopes of Gargano and in the southern portion of Salento. We can see a type of coast crags in San Dominio Island. Next, high rock coast di Rodi Garganico, and next we can see a rocky coast with Pebble Beach in the foot, Baia delle Zagare e Mattinata. Next, we can see low rocky coast in Torre San Sabina, and then another type of coast of sandy beach Ginosa Marina, and finally anthropic area in Port of Brindisi. We have carried out this in these laws, that the Apulian coastal are indicated in kilometers and in percentage terms. With the next slide, we can see four types of coast are majority in Puglia region. now we can cross the lithology data with those of type of ghost, and we can see that we have 23.76% sandy beach, 26.20 rocky coast, and 30.77 crags, and 29.46 anthropic area walks. In Puglia, 4 types of coast make over 93% of the Apulian coast. The following lithology were not found along the coastal strip, and then we have the prevailing lithology in percentages. Sandy beach are made over of 78% of lithology, 8. Rocky coast 31% of lithology, 1, and crag up 42% of lithology, 1, and 35 of the lithology, 2. The anthropic area are made mainly out of the lithology, 24% 7 lithology, 25% 8 lithology, 19% 1 lithology, 18% 2 lithology. In this slide, we can see for the domain lithologies along the natural coast development grouped by provinces, and under we have the lithology, the hydrogeological map. Now we can speak about the CARD project, the National the geological data collector and comparison and constitute the ISPRA geological database. In the Puglia region, the CARD project was interrupted by due to the lack of funding and resumed in 2020. 4 years are foreseen for the realization of the sheet, therefore, out of 54 sheets needed to cover the entire Apulian territory. 39 sheets have not yet been funded. This slide shows the progress of the project. We have the sheet Ugento compared with the same line of digitalized new coastline. We can see that we have such some stretch of coast in erosion and other in accretion. We can see in 70 years ago the state of the area, and now in the state of urbanization of area. We can see the area of accretion, and we can see the area of erosion. In the accretion area were measured in square meters, and the erosion area in this stretch, of course, were measured in 259.268 square meters. In some points, the erosion can be calculated in more than 115 meters. The new digitalized coastline includes also the length overall anthropic opera. The numerical and morphometric analysis show the anthropic opera length in the coastline to 29%. Is comparable type of natural coast prevalent in Puglia, local cost 26% and sandy beach 24%. Between Torre San Giovanni and Torre Vado appears clear the correlation from anthropization and the coastal dynamics of the last 70 years. And the coastline present in two cartographic database analyses should be the same so as not to create confusion to the planner and manager the territory. The same cartographic database should be updated periodically and actually the same. The same cartographic things cannot be mapped in a different way, in official thematic message of different modes, but only allow different view and will more information as the scale of representation increases. Generalized for small scale view. I have finished.
Okay, thank you, Mauro, for your kind presentation. Does anyone have any question? Mauro, I have a question, curiosity. If you can explain me, I have seen some incongruencies in your work because I think you compared two kind of data at different scale of work. Do you compare? Probably I didn't see well your presentation. You compared scale at different from IGM and orthophoto that are different scale, no? To derive the cost line.
Yes.
Probably I have seen bad.
Yes, the different in the is orthophoto and the IGM table, the 70 years ago.
And so, yeah, but as you can mention, there are two kind of accuracy in both the data, geospatial data, because we are thinking about scale 1 to 15,000, and at the same time, orthophoto are at 5,000. And so I think that some meters of errors are inside in the results. Probably you need to have some to verify this problem. Okay, thank you, Mauro.
Thank you very much.
For the presentation. We have concluded the second session related to GRMM. I'm very happy to see you, to have the participants all together in this session. I invite all the participants to attend the next section in the afternoon. And I thank you very much for joining this conference, and I hope to see you to the next ICCSA conference. See you in the next ICCSA conference. Bye-bye.
Thank you. Bye.